Ну,
Да.
собственно, объяви тогда, и я начну.
Okay. So eventually we can begin. We have the third and the last, as I understand, part of Volodya's talk on modified Bessel equation and a lot of matters related to it. Quite interesting. So, Volodya, please, you are welcome and begin.
Okay, so thank you very much for your invitation again, and I'm sorry for these technical problems, which unfortunately out of my power. And I will remind again what we discussed last two times. So we discussed so-called N-Bessel equation. N-Bessel equation, it's equation which I'll show you this N-Bessel equation. I go in opposite side. So this is the equation which we discuss. This so-called quantum Pn-1 operator, or N-Bessel equation in my terminology, and the analytic solution of this equation it's the following power series. It was like the usual Bessel modified, slightly modified, but instead of 2 here, degree n. And we discussed last time the product formula for these solutions in 2 different points with the same eigenvalue. I put this eigenvalue for simplicity equal to 1. And the product formula gives this double series in x and y with nice binomial product coefficients. And we discussed that we can also represent this function in the form of Cauchy residue theorem, in integral form as a residue of this differential n-1 form with toric or d-log differential measure, and the exponential of this Laurent polynomial of n-1 variables. This also sometimes for reasons of similarity, this Laurent polynomial called Dwork polynomial or family, because it contains also small parameter x, which is our argument. And physicists often call this Laurent polynomial superpotential of some Landau-Ginzburg models for the reasons which I will not explain. So if we take this product, we also can represent it not only in this series form, but also at the convolution with some kernel. And the kernel will be my main interest today. And this kernel, it's homogeneous function of 3 variables x, y, z, because we express this product in the convolution form with the same function in the point z. And when we go to affine coordinates big X, big Y, which X over Z, Y over Z, then the series form for this kernel simplified enormously. And what we are interested in now to understand the singular loci for different values of n, and this singular loci are very nice polynomial which have very nice algebraic form. For example, for n equal to 2, I showed you that this polynomial is quadratic in x, y, z, so it's kind of conic in P2, and this conic nicely factorized if we have so-called Kummer pullback. This Kummer pullback, when we replace x, y, z by by u square, v square, and w square, so we have quartic, and this quartic factorized in the product of 4 linear terms. It is immediately, you see that this configuration is a configuration of so-called Heron formula type, the formula for area of triangle with u, v, w as sides, with the coefficients 16. This is usually area, it's square root of this, so it's square in square, and 16 comes from coefficients 2, because you have here not half perimeter but full perimeter, and the other formulas also have coefficient 2 in front of it. So it's a natural expression for this configuration. It is nicely also compatible with n equal to 3, n equal to 4, and higher n. For example, first statement about any n, that this kernel has so-called motivic nature. It means that it is a period type integral for some hypersurface. This hypersurface, which we denote here by w sub n, depends on 3 parameters, x, y, and z, 3 variables in P2, and also on n-1 parameters which form this kind of Laurent polynomial in big y's, y1, n-1. And this configuration is a hypersurface in torus, hypersurface in torus, this family of hypersurface which depends on x, y, z, and the torus, it's a n-1 product of spheres in the space with coordinates y1, yn-1. So the kernel can be computed by this residual formula. We have this toric D-log measure, and we have this locus of zeros. It means this hypersurface, family of hypersurface, which depends on x, y, z. So we proved that this is a very nice integral expression for this kernel. And also we studied the zeros of the corresponding homogeneous expression for hn. So this is x, y, z, and then when we go to a fine part, we have this hn of x and y, when in P2 we divide by z. So we have the curve, a rational curve of degree n with double points, number of double points is n-1, n-2 over 2. And these double points intersect the coordinate triangle xyz equal to 0, x equal to 0, y equal to 0, z equal to 0 in the midpoints. And the expression is a symmetric polynomial which factorized by the following way. We go to Kummer pullback of degree n. It means we replace x, y, and z by u to n, v to n, w to n, and this formula can be written as a product of linear combinations of u, v, and w, and coefficients of these linear combinations running over all nth root of unity omega and eta in front of v and double u correspondingly. More concretely, you can see that for n equal to 3, the irreducible part has this symmetric form. For n equal to 4, this symmetrics, they are all symmetric in x, y, and z. Here it is written in general way, and here it is written like polynomial in fixed variable, namely polynomial in z variable. Why it is written here in this way? Because when you write it, you see that you have algebraic algebraic equations in z. This is a quadratic equation, and this is cubic equation. All these equations, they are discriminants. They are discriminant of quadratic. Here it's discriminant of cubic, and here it is. We can prove that all such zero loci, they are given by some discriminants, and it is not by just by chance. It is always the following reflection of this factorization. So, for example, I will show you. Oh, it is not here. I will show you. I prepared for today some more explicit formula. I'll come back. Don't worry. Oops. No. No. Sorry, my friends, because I prepared it on my iPad, and but I will try to explain it orally. So if you look, for example, n equal to 4, for n equal to 4, this configuration, this one, you can write as a polynomial in z, and this polynomial, which is general in x, y, z, this polynomial can be also factorized if you take, instead of x, y, and z, this Kummer pullback, and then you can factorize it in the product of 4 linear terms, like in the case of n equal to 2. And also you will have 6 quadratic terms, and these 6 quadratic terms, they are conics, and these conics you can also factorize in linear terms, but the 4 linear terms, they are real, and the 6 conics, they are factorized only over C. It means that you can use this square root of 4. You have two real roots, 1 and -1, and you have 2 complex conjugated roots. So you can also split it, these 6 conics, in the product of pairwise linear terms, but with complex coefficients. And it is a very nice representation for some special K3 surface with singularity. Of course, it will be singular surface, and this surface is a kind of Kummer space, Kummer surface, and it has 16 singularities, because you have 4 linear terms, and this conics, they split in 8 or in 12. They split 4 and yes, in 12 linear terms, and so you have 16 singularities, and these 16 singularities correspond to the singular points of this Kummer space. And if I remember properly, Picard number of this case 3 equal to 9, and the corresponding differential equation which annihilates this kernel, it is a very nice Calabi-Yau differential equation, which I discussed, belong to the class of differential equations which I discussed last time. And the last, what I want to say about this nice kernel loci, it is that they define so-called Buchstaber-Ries multi-valued group law. So when you write it in this form of algebraic equation, you see that for n equal to 2, you have two roots depending on x and y. Here you have 3 roots depending on x and y, and etc. For example, here you have 4 roots depending on x and y. And then in each case, there is a construction which described by Buchstaber and Ries, how to define n-valued group law for n equal to 2, 3-valued, 4-valued, and for any n, this loci defined n-valued multi-valued group. And it is amusing, and the sense of this not completely clear at the moment. It looks like I'm using coincidence, but maybe there is something, some algebraic, deep algebraic reasons behind of this. Is what at the moment I can say. Okay, so this is a duplication kernel. It means that you go to diagonal and take the product of two identical solutions of your Bessel equation, then you obtain this nice power series with binomial type coefficients. And this binomial type coefficients for n equal to 2, they, as I explained last time, they correspond to this generating function intimately connected to Catalan numbers. And this I spoke about it last time. For n equal to 3, this diagonal kernel K3 is a solution of this equation of order 2. This equation, Picard-Fuchs equation, which calculates this, is order 1, and this is the order 2. This equation has a special property. It's a Hoyne equation. It means that it is represented in the form which also I described last time under the name of Kontsevich polynomial trick. And generically for any n, these kernels, they are also relates to period of Landau-Ginzburg model with this superpotential. You remember that in my example, I presented it like a family of surfaces in P2, and here it is just a refined superpotential for Landau-Ginzburg model we get. So this interesting coincidence that if you take the Dwork type hyperpotential and take the kernel, then you obtain the same series for this integral representation and for this integral representation. So it is our discovery is that for different type of hyperpotential, you can get similar formula for periods and this. Okay, then I told you last time that it is possible now to relate it to standard arguments of so-called mirror symmetry paradigm. So it means that we can describe the Newton polytopes of our superpotentials, and if they are good, then the corresponding surfaces can be compactified to real smooth Calabi-Yau varieties, and this, for example, for the case n equal to 3, we have checked that our examples, they really give the famous before in the papers of Viktor Batrev, the corresponding Calabi-Yau is a compactification of the surface which we obtained from our n equal to 3 case. So it's a double W3, our kernel, and this is dual polytope. So this is, but it is I can't say that it is true for any n, but for n equal to 3 it is. Why I can't say it for any n? Because for any n, the property of my kernels, they are not completely similar. For example, the first small number of n equal to 2, n equal to 3, n equal to 4, n equal to 5, they satisfy to some equation which we can call Picard-Fuchs because they have MUM property. I remind you, MUM property means that they have in the origin the maximally unipotent monodromy, and the corresponding Jordan block for monodromy is an upper triangular with good exponential coefficients. For example, for n equal to 2, you have the equation order 1, which annihilates the kernel, this function, you remember this function 1 over square root of minus 4t, and the origin is a good singularity. And for n equal to 3, n equal to 4, and even for n equal to 5, which is annihilates by the equation of order 4. So theta, I remind you, it's Euler differential or logarithmic differential t d over dt. And then you think that it will be similar for any n, but the experimental experiments with computers show that it is not so, unfortunately. So if we consider the differential operator which annihilates our kernels, then the first 5, as I told you, they have very good behavior in the origin. So you have two-dimensional Jordan block for n equal to 3, one-dimensional for n equal to 1, evidently, and for 4, three-dimensional, four-dimensional, and it is single block. But for n equal to 6, you have this phenomena of appearance of the second block. So you have one extra eigenvalue 1 and 5 to 5 Jordan block. So for n equal to 6, your MUM property doesn't work. So your operator, which annihilates K6, it is not Picard-Fuchs. And so we can't expect that it has completely the same behavior like Calabi-Yau differential operators. Then this phenomena repeats until 9. It means that until 9 degree n equal to 7, n equal to 8, n equal to 9, you have two Jordan blocks. This Jordan block of size 6 times 6, Jordan blocks, Jordan block 2 times 2. So this is just one number appeared. Here is the Jordan block with unity on diagonal 2 times 2. Here it's 3 times 3, and here it's 4 times 4, second block. And for n equal to 10, the third block appears. And then we can prove that it goes with periodicity 4. So it means the next catastrophe, you see here we have 6, you have now 10. The next catastrophe will be when n equal to 14. Until 14, everything will be like for 10. And for n equal to 15, new block, the fourth block appeared. And this is a general property. But anyway, for up to 5, everything is okay. So we can try to consider this Picard-Fuchs operator of degree 4, which here it is written not in Euler form, but in normal form, with this locus of singularities in front of dt to 4, this one, and it has degree. You see, it has a degree 12. This polynomial, and but the point has maximal unipotent monodromy, so we can try to find. So we can try to find Frobenius basis of fundamental solutions. So, and like in the case of good Calabi-Yau differential operator, for this differential operator, we can play the same game with mirror canonical coordinates and take the Frobenius basis with integer coefficients of analytic solution, and the second solution, which contains logarithmic term, is no more integer. Third also in logarithm in degree 2, and logarithm degree 3, of course, all of them are only rational coefficients. So we can cure it in the same way, introduce this Yukawa potential, which is a second order Q operator of the ratio phi2 to phi0. We obtain this rational coefficient series, but if we pass to Lambert development of this series, we obtain up to the factor, rational factor 5 to 7, integer numbers n sub k, this with common coefficient k3, and this n sub k, they play the same role like instanton numbers for famous quintic operator in the case of Candelas, De La Osa, Green, and Park's construction of Gromov-Witten invariants. But another side of possible mirror conjecture, of course, it is not mirror conjecture, it is analog of it. Another side, it is still unknown. So we have integer set of unknown. So we have an infinite series of integer numbers, which is not in OEEs, and what the sense of it, we don't know. And this is the last possible, I would say, analog with mirror for these kernels. But we can continue to produce some interesting numerological invariants. For example, we can consider our n equal to kernel and express it not as a series in one variable, but we can consider it like a development in one variable with rational function coefficients over z minus 1 in the denominator. For example, we can write it like this: 1 over z minus y, then some function y plus z over z minus 1 cube, then some square function over z minus 5, etc. And then we discovered that all nominators, they are symmetric, and coefficients of these symmetric expressions, they are complete squares. 4, 9, 9, they are palindromic. It means that they are symmetric from y to z and from z to y. And also all coefficients of these palindrome polynomials, they are complete squares. So we can write it in this observation, we can write in the following way: write this series over odd denominators in z minus y, then the polynomials which are coefficients of this development, they are always palindromic and they are always monic. So they can be written in the following double series form, and we can consider the as a generating function of Pascal triangle. You remember that we have this 1, 1, then 1, 4, 1, 1, 9, 9, and etc. So we have, for these coefficients of generating function, this Pascal triangle. And then we can write very nice differential formula how to get all these coefficients. So they can be computed like, it's a just very simple combinatoric trick. We can compute it by this formula, and this nice observation gives possibility to express these coefficients as a difference of two values of combinatorial. So this generating function we can write like difference of two hypergeometric functions, f21 and f32, with such monic polynomial coefficients in front of it. But it is not the end of the story. We can now consider n arbitrary and write the same, but not in the odd number degrees of z minus 1 in denominators, but mn plus 1. Then we obtain again palindromic property for these new coefficients of new generating function. And we obtain new n degree Pascal triangle, and we can get these coefficients in a similar formula. For n equal to 3 and for n equal to 4, this some numbers which we obtain in this series, they are known for people who monitoring this OEE's site. So for n equal to 3, we have a sequence number A18, 15, 44, etc. And they relate to so-called Narayana and Fresnel numbers, which are some generalization and relatives to Catalan numbers. What about the properties of this new series? So if we take these coefficients for n arbitrary, we can write nth Dwork family. So instead of first degrees of x1, x2, xn, we can take nth degrees. It's a real Dwork family of hypersurfaces. And we can consider nth degree of Landau-Ginzburg potential, which before was just the sum of this, of the degree 1. And we have verifications that there are integrals representations for this Landau-Ginzburg potential similarly to one not multinomial, but for not only for monomial, but also for multinomial these families of hypersurfaces. When I understand under multinomials, any degree n. And also we have the following further generalization, which we didn't study experimentally too much. Namely, what we can do. We can, instead of Bessel and Bessel, write so-called Pochheimer perturbation. It means that we can, instead of nth degree of Euler derivation, we can take this Pochheimer operator, which means that you take Euler, then Euler plus 1, etc., up to n minus 1. And we have, of course, a very concrete differential operator, so we can consider the corresponding equation similarly to Bessel, but not Bessel. And we can find the analytic solution of similar form. Instead of this, for n Bessel, we can, for Pochheimer, this solution, and the denominator will be product of Pochheimer's indices. So then we can compute the kernel, also develop it in the similar way, and then we obtained the coefficients of this polynomial, which are well known. They are so-called n Narayana numbers. So we have generalization of duplication, Clausen type formulas. What we don't know, we don't know if there are some motivic, if there are some periods interpretation for these kernels, for this series. This we don't know, and this is open question at the moment. That's what I supposed to tell you for 2 times, but because today we have still few minutes, I can add you.
We have more than few.
Sorry, I don't hear you.
We have more than few minutes.
Yes, so that's why I decided to tell you a little bit more about to Bessel. In fact, I told about it a couple of years during the COVID, but maybe not everybody heard about it. So I want to remind you the prequel of my story. This is a classical Bessel equation, standard, this one. This is my favorite change of variables for imaginary arguments of Bessel equation. Then we have so-called modified Bessel function of first kind and degree 0, which is just a Bessel function of the first kind with imaginary argument. And we go from usual argument to square root of it, times 2. Then we simplify the power series representation, and I have my hero G2. And this is a so-called degenerated hypergeometry. and people called it, as I told you, Klosterman equation. So this Klosterman equation, this is my equation theta2 minus u, and it defines from modified Bessel by sign. If you look modified Bessel, then it is just defined by sign by this square u, and this square u, and this no square. Now I want to tell you about one more feature of this to Bessel. Namely, it relates to so-called.
Volodya, I'm sorry. Is it possible to to magnify, because now it's
this
better.
One?
Yeah.
Sorry, it is possible, but it is possible, of course. Okay, is it better?
Yes, thank you, much better.
Okay, now I want to remind you of the link between these Bessel operators and so-called generalized translation or generalized shift operators of Delsart and Boris Moisеевич Levitan. In fact, I discovered, I understand that maybe it is not very popular in this seminar, but sorry, I have some question.
It's the visibility of the slide, that's all.
Okay. Okay. In fact, I have discovered when I started to work on it that there is a big input in the theory of this special function and product formula from Gelfand school. First, of course, I should mention Felix Berezin, who in his thesis, he wrote very beautiful thesis about links between representation theory and harmonic analysis. And then by Naum Vilenkin and Mark Graev, and Gelfand participated in all these works also. But the work of Levitan is very special, because Levitan generalized the approach of French mathematician Delsart and put it in the relation with the theory of Lie group and Lie algebras. Namely, what is the Levitan approach to generalized shift operators? First of all, what is the generalized shift operator? Let's consider any variety, just some abstract variety X, and we consider commutative algebra of complex valued function on X. Then it is maximally abstract notion, this operator of generalized translation operator or generalized shift operator. First, it is operator parameterized by points of my base variety. So for any point y, I define the operator t to y such that this operator is a linear. So for any complex coefficients alpha and beta, it is just a linear operator acting on functions over x. Then there is a point in my variety such that the operator, depending on this point, acts like identity for any function. And then if we have some topology, and then we can consider this operator for point y, t to y, applying to a function f in some point x from big X as a function of two variables x and y. And I will always think that this operator t defined in such a way that this function is a continuous function in x and y with respect to the topology of my variety x. Then the next axiom of Levitan is its associativity axiom. It means that if we apply this operator in the point x to my function in the point z, and then we take operator in the point y and applying to this on x, then we obtain some function of x, y, and z, and it is the same function which we obtain if we apply instead of t to x, t to y to f of z, and then apply this operator depending on x.
Volodya, I'm sorry. First of all, I do not understand what t with sub and superscript mean.
So t to y, it is just operator, just a family of operators parameterized by point of x. So if
Yes,
you yes, and then subscription means that it acts on x. So when you take this operator tx to function in point z, you obtain something which depends on x and z, and then you act by shift to y, but only on x. And here is vice versa. You apply before y to the function of f of z, you have two variables y and z, and you apply it on z.
Yes. Now I understand.
And so you have just two functions of x, y, z, and they are the same for any x, y, z, and for any f. And it is naturally to call associativity. But also we can, it is not necessary, but it is sometimes it is very often that operator is such that this application 2x, tx and ty, it is the same that application ty, tx. And then we will say that the family of operators is a commutative. So if we have these four axioms and sometimes fifths, then the family this is called generalized shift operators of Levitan-Delsart. They were very modest, Levitan and Delsart, and they were not, I would say, they always consider very simple varieties. For example, they consider variety x half line r sub plus, or line, or a part of line, a segment AB. That's what typical typical variety in the examples of Levitan and Delsart. And then the following statement is quite useful. It was one of the main results in the first paper of Levitan, that if we take one of these three varieties, x, then consider a family of differential operators in the variable small x, which linear operator of order 2 with coefficients alpha of x, b of x, complex valued functions. and this is a linear differential operators, can give you the following generalized shift operator. Namely, let's introduce this operator family T to Y like a solution U of xy of the following Cauchy type problem. So we apply this operator L in X, and you obtain the same if we apply this in Y to U. And the Cauchy data is the following. If we take X equal to 0, oh, sorry. If we have, I'm sorry. If we have this x equal to 0, we have f in y. And if we have derivation over x in x equal to 0, we have f of y multiplied by some constant. So this solution u of this problem define this operator. It's a theorem. It's a Levitan theorem. Now, I remind you my philosophy with multiplication product. So we have for any differential operators and for any eigen value problem solution phi sub lambda of x, we have multiplication kernel k, and such the k doesn't depend on lambda. And what is interesting, if we apply my operator in x to the product phi sub lambda in x, phi sub lambda of y, it will be the same like application of this operator in y to my product. And we have products phi lambda of x, phi lambda of y with the same eigenvalue lambda. Then we can put in my multiplication kernel formula this, and we obtain the following, that it is equal to lambda times my kernel with phi lambda z, and it is the same like integral with kernel k, but with function instead of phi lambda of z, L over z applied to phi lambda of z. And this is by natural guess, you can call it the application of dual operator lambda to phi lambda of z. So it is a dual in the usual sense. So if you have this multiplication kernel, you can always consider this formal manipulation, and applying this formal manipulation, you can define the following operator of a generalized shift operator in the case of Bessel. First, if you look the Bessel operator, you can see that this operator, people who studied shift operators, for example, Buchstaber and his student Holodov, they recognize this operator like the first invariant operator D1. They called it first invariant operator D1 with eigenvalue 1. Then the shift operator T V U in the point, this operator defined by V, we applied it in U to some function f by the following formula. We take the coefficient of G0 of u, it's a G0, it's a Bessel function development, and take our D1 operator and applied it to f of u. So this is a definition, and the property of this definition gives you a possibility to write it in the multiplicative formula way. Namely, if you look very attentively to this operator, you will see that it is a kind of radial part of Laplacian operator on the plane. Namely, this one. Now, instead of u, I will write r, and u and v, it will be plane coordinates. Then Laplacian for any function big F of u and v, radial part of it you can write like application to small f of r, which r is the square root of u and v, or like application of this D1 Bessel operator. So we obtain by our definition this operator of shift operator on R instead of before I wrote U, but now I write R. And we have, instead of this, we have Laplacian operator to function f of uv. Or if you want, you can write it like delta f of r, delta k f of r. Now, let's define the following, let's verify the following property of it. Take our shift operator in application to G0 Bessel in U. I would like to write it without I. You see, it's in real U and V. Then you have this product of Sonnen-Gegenbauer, and I don't know the formula of Sonnen-Gegenbauer. I just want to define this product formula and to compute it in the following way. We can use the mean value theorem for unit circle. Then we take internal in the disk point inside of this circle, and take this product by this mean value theorem. This is just G0 in the middle point of this circle. How I can interpret it? I can interpret it in the following way. So, oops. Again, you see, it's very bad. So we take this internal point denoted by W, which is square root of U square plus V square minus 2 times UV cosine phi. And then our formula will rewrite in this way. But now we want to go from the measure, angle measure d phi, to measure related to W. And then we take the cosine theorem, this this x, it will be our, you remember, it's our plane, and this our plane we can consider like a symmetric space, with respect to rotation group action. And then the measure dW how to compute it? You just take the derivation of the square root, it's 1/2 square root, and then you take the derivation of expression under the square. You have 2 times uv sine phi d phi. So you want to compare the derivation by phi and derivation by the differential of phi and differential of the dw. And the coefficient of this, it is the uv sine phi. It's a formula for area of triangle. And this is w. So you have the relation w times dw divided by 2 area of triangle, or it is just, so d phi and the dw, they differ by this Heron expression in u, v, and w. So we are again arrived to our second Bessel Sonnen-Gegenbauer kernel, KUVW, and this is our conic. You remember this in UVW, it's in square, can be written like 16 airs of triangle, and it might be factorized. So here I just prepared some explanation how this relates to the measure of to this small arc which correspond to angle phi divided by p. So that's why this formula really gives you formula of Sonnen-Gegenbauer in the limit u plus v, u minus v, because from the triangle inequality, w is between module u minus v and u plus v. And it means that the measure which you want to use, this d phi, it's w dw divided by p two squares. You should multiply by the characteristic function of this interval, because w has sense only under this condition for triangle. So you should multiply it by 1 if your w satisfy to this. So it means that we have some characteristic function of our segment u minus y, u plus y, and it means that your measure, in fact, it has some sense of characters, of character. This very trivial example of this character, but it corresponds to the character of representation of your rotation group anyway, in some sense. It is just a remark. Okay, so this what I told you many times. It's a Kummer pullback, and this Kummer pullback gives you formula which we saw before. Okay, so this again, this Heron configuration, I remind you. And the last, it is how to write this equation in the form of so-called Bessel connection. This is a very popular subject of the last few years of studies to study number theoretic aspects of this n-Bessel equation. And one of the most interesting aspects is consider this corresponding linear system, and this linear system can be interpreted like a connection of Rankine connection on P2. Hello. I'm sorry, I suppose that maybe some of you. it's a question, if there are an operator that doesn't satisfy associativity of commutativity. Of course, it is both questions I can answer. Thank you for your good question. The first question, of course, there are non-commutative operators, but associativity should be. I don't know examples of non-associative shift operators, but non-commutative, yes. And the second question, Heron formula exists not only for flat spaces. It is also exists in spherical form, and there are generalizations for hyperbolic measures as well. So it means you can write for spherical Bessel functions the product, and you can write the product for hyperbolic Bessel functions. So it is a subject of many papers of 60s, 70s, and 80s. People wrote different expressions for kernels for Bessel functions in spherical representation and in hyperbolic representations. And moreover, there are generalization of these product formulas because it is just one simplest instance of general theory, which you can find in the book of, for example, of Vilenkin or Klimek and Vilenkin, representation theory and representation theory and special functions. There are two beautiful books, one of Vilenkin and second Klimek and Vilenkin, which is one can say extended 20 years later edition. And there are products of many special functions, Airy functions, Whittaker functions. As I started my talk 3 weeks ago from this diagram of confluence from Gauss to Airy, and for each of such functions you can find the corresponding products, sometimes very complicated. Also, there is a generalization for so-called Dunkel operators instead of solutions of differential operators like the Bessel differential operators. You can consider differential operators with non-local differential operators like Dunkel operators, and there are analog of product formulas. And this also very popular subject of the last 10-15 years. Well, I think that now it is all. At the moment, I have.
Okay, well, thanks a lot. Questions, remarks?
Just the last formula, which I showed you this connection, not for nothing. It is just a remark that this also is a generalized hypergeometry for n bigger than 1. You see?
Yeah, we see that.
Just it is another instance of this series.
Thanks. Questions, remarks?
If you want some literature, I can give you references for these special function products for this hyperbolic Bessel, spherical Bessel, and there are some interesting interpretation of kernels also, like a triangle area, if you want, spherical and hyperbolic. Yanis, do you know my email?
Volodya, there is a message from Yanis concerning.
Yes, I see. I ask Yanis, if you have my email, write me yours, and I will send you all references.
Maybe you will send it to Alec in the form of PDF.
To Alec, okay.
And he will add it to
okay.
the entire material of your lectures. It will be
I want to say something. Just a moment. I want to say something. I think that in a few days we will put in archive our paper with Ilya and Duko, and in this paper there are references to all this stuff.
okay.
And I'll send Alec the link to this.
Yeah,
Okay.
okay. Yeah, perfect. Okay, Volodya, thanks a lot.
Thank you.
So
Thank you for your patience with.
yeah, it was a marathon. Okay, so the next time we meet is April 17th, and we shall have a talk by Gerard Helming from Korteweg de Vries Institute in Amsterdam. So everyone is welcome, and thanks for attending, and goodbye.